Well, it's a pleasure to have the opportunity to tell you a little bit about our work in silicon photonics, specifically for trapped ions. I think maybe to start us off, we could do a little show of hands. Who's familiar with integrated photonics or silicon photonics? Kevin's waving in the back. Okay, we have a couple here. Wonderful. Well, what we'll start off with today then is an introduction to silicon photonics, and maybe I can introduce a lot of you to this wonderful field of integrated silicon photonics. We'll then take a look at what we can do when we use integrated photonics to address trapped ions, and then I'll briefly mention some of the other work happening in our group, the Photonics and Electronics Research Group. So this will be a little bit of a switch in topic. The last speaker was really talking a little bit more about algorithms and how you do these advanced gate operations, things like that. Now we're going to switch more to the engineering side of things. How can we deliver light to interface with different types of qubits, and specifically trapped ions in this case? So let's start with an introduction to silicon photonics. So for those of you who are not familiar with silicon photonics, the general idea behind our field is that we want to take standard CMOS fabrication processes and repurpose them to create optical devices and systems on chip. So on the left-hand side here, you can see a standard bulk CMOS transistor. Normally when you have a CMOS process, you would use this process to fabricate these transistors that are going to do electrical switching and do the standard computation that we have in our classical computers here. So you'd have a silicon layer here. This is if you took your computer chip, for those of you that are maybe not as familiar with the hardware side of things, this would be if you take your computer chip and you cross-section it in half, this is what one of these little nanoscale transistors would look like. So you have the silicon over here. Then you would have regions of what's called doped silicon. That's where you take the silicon, you bombard it with dopants. And then you'd have metal coming down into contact with those doped regions. And what that allows us to do is on those metal lines actually apply voltages and get switching of the transistor. That's what allows us to do our normal classical computing gates, right? That's what allows us to do classical computing. So what we can do is we can take all these layers that you would normally use for your transistor and repurpose them to create optical devices on chip. So for example, here you would see a cross-sectional view of a silicon photonics optical waveguide. What this is going to look like is here in this cross-sectional view, it's a little rectangle. If you actually took a top-down view on your chip, what this would look like is you'd have that little rectangle and it would be a long strip of that rectangle on your chip. And if you took maybe electromagnetics at some point in your engineering career, you would have learned that if you have this strip of dielectric material here, and you put in some electromagnetic wave, in this case it would be an optical wave, into that waveguide. That waveguide is going to confine the light on your chip in that little strip of silicon, and it's going to guide the light down the chip. So we have this way of confining and guiding light on our CMOS chip here. Okay, so we're confining and we're guiding our light, but we don't want to just have the light on the chip, we want to be able to do operations with this light. So we need to have some way to modulate the light on the chip. So what we would do is we could maybe take this waveguide and we would create an active electro-optical modulator. So you'd have your waveguide here that's confining and guiding your light, and then you extend it on either side. And then on either side there, maybe we'd put some of those dopants in that allow us to have electrical properties in this silicon. And we place metal down into contact with those dopants. And now we can apply a voltage across that waveguide. And through things called the thermo-optic effect or electro-optic effect, you're going to apply that voltage across that doped region, and it's going to change the properties of your waveguide. And now when the light goes through the waveguide, it's going to either slow down or speed up. So you have this way of changing how the light passes through the waveguide. We call these electro-optic phase or amplitude modulators. And then, okay, we can guide the light on the chip, we can modulate the light on the chip. Now we want to interface with the surroundings of the chip. So to do that, we would pattern some more interesting, more complex devices. Maybe something like these grating antennas, which we'll talk about in a few slides again. The idea there is you have your waveguide on the chip. Now all of a sudden you want to scatter the light up and out of the chip to interface with different things in the environment. For quantum computing, that thing would actually be the physical qubit that you're trying to interface to. So by taking these CMOS processes and using them to create optics on chip, we can take optical systems that were once complex and bulky. Maybe they would take up an entire optical table in a research lab or a ton of optical fibers all connected together. Well, we can take these optical systems and now we can compact them down into these little millimeter scale silicon photonics chips. A very small form factor. Also, by taking advantage of CMOS fabrication processes, right, CMOS chips are fabricated on the wafer scale. You can see up on the top left here is a photograph of a CMOS wafer that was fabricated in our lab for silicon photonics. Well, these CMOS fabrication processes, they're fabricated on these large 12-inch wafers, which allows us to really scale up how many of these chips we can fabricate at a time. So it's a way to scale up the manufacturing, both the yield and the number. And then finally, by integrating these optical devices onto chips, we can enable new functionality that was never before possible with bulk optics or fiber optics. And you'll see why this is so important when we start interfacing with these different types of qubits. Maybe I'll pause here if there's a question or two, just to make sure we're kind of catching everyone in the audience that maybe hasn't seen this field of integrated photonics before. Absolutely.
And how you get the wave to go down low end of that, and because I've seen it in other areas, radar systems.
Oh yeah, that's essentially waveguides for RF. Yeah.
So how does that become a qubit? My understanding of that is missing, and that's key to almost everything that was talked about today.
Oh yeah, so far, no qubits. This is all classical. So far, we're just putting classical laser light on this chip. You'll see in a few slides how we can actually use this then to interface with qubits. So hold that thought for maybe 5 minutes.
Forgive me, but if I could talk with you on another day, that would be appreciated.
Awesome, yeah, absolutely.
Thank you.
Any other questions before we keep going?
Are you essentially creating like gates through this?
You're essentially you're trying to take functionality that you would normally use, maybe an optical fiber or bulk lenses, and you're taking that and putting it on the chip. So far, we haven't yet touched the quantum side of things. We're just thinking about how can we get light on a chip and create these optical devices on the chip. So maybe let's keep going and see how is quantum computing going to come into this field of silicon photonics. So in general, this field of silicon photonics actually came up because of the problem of optical interconnects. There was a need to take data, move around lots of classical data to move data on and off the chip in large volumes. And silicon photonics really came about as a field because there was a need to do all this data movement in the optical domain where we could have faster speeds and lower losses. And because of this, the field of silicon photonics kind of rose up, and there was a lot of infrastructure put into place on how can we fabricate these chips, how can we create platforms for silicon photonics, all still classical, but there's a lot of money and infrastructure poured into this field. And now we can take this idea of integrated photonics and apply it to many different other application areas. So things like LiDAR sensors or AR displays, free space, classical communications, biophotonics interfacing with the body with optics. But relevant to this workshop today is that we can actually use this field of silicon photonics to interface with different types of qubits optically. And the qubit that we're going to talk about now for the next 30 minutes is the trapped ion. So that's where now we're actually going to bring in the quantum computing side of things. So maybe show of hands, who's familiar with trapped ions? Okay, so now we have about maybe a third of people. So trapped ions are a very promising modality for quantum computing because they have very long coherence times. They're fundamentally identical, and they enable high fidelity gate operations. So maybe before I switch to the next slide, just because a good chunk of people didn't raise their hands for familiarity with trapped ions, let me step back and just introduce you to what a trapped ion would be. So if you think about back to kind of your basic quantum physics class or maybe your chemistry class, when you have an atom, right, there's neutral particles here in the center. And you might have an ion where you have some charged particle that's hanging out on kind of the highest bands of this atom. And this little charged particle, this ion that's hanging out here, depending on what band this ion is sitting at, depending on what that state of that ion is it sitting at a lower energy level or a higher energy level? That's effectively going to be the 1 or the 0 in your quantum bit, your quantum computer made out of these trapped ions. So we have this ion sitting here, and it's going to be in these different levels. There's going to be different states it can be in. So there's this little charged particle, this ion. It's going to be in these different states. How do you actually switch between states? How do you read out what state this ion actually is at? You need to be able to use, or these states are separated in energy by exactly optical wavelengths. So you need to have some way to interface with this little ion qubit optically, to actually switch between the 0 and the 1 state, or to read out when this ion drops down between states, it's going to emit a little photon. You're going to need to be able to interface with that ion optically to even read out what state that ion is in. So there's this need for trapping that ion there to actually create your qubit, and then some way to interface to this ion optically to actually do all the different operations for this quantum computer. So now let's take a look at what does this physically look like. So at first, we need to have some way to take that ion and to trap it in space. So first demonstrations of this look something like this. This is called a Paul trap. These are long metal rods that have DC and RF fields actually flowing through them. And they're oriented like this, where this would be a cross-sectional view if we cut this guy, this physical guy here. You'd have these metal bars here. Red is the RF potentials, gray is DC potentials. And if we apply just the right voltages here, we're going to create the correct potential to actually trap this little charged ion here in the center of this trap. This is great as a first demo, right? But if we want to create a real quantum computer, we need a way to take this system and create it in a more integrated, more scalable way. So the next huge innovation in this field of trapped ion quantum systems is to take this really bulk system, this Paul trap, and integrate it down into a chip. So the idea is, can you take these metal bars, these electrodes, and actually kind of flatten them down and pattern them on a little chip? This isn't necessarily now at the stage yet where we're at CMOS level complexity, but this could maybe just be a little silicon chip here, and these could be little metal electrodes now on top of the chip. These electrodes are now going to be powered with those same fields to create the potential to trap this ion now above the chip. This is physically what that looks like. We have this little chiplet down here. This is from an image from Duke University. A lot of this work has transitioned to IonQ, which is a big company operating in this space. So they have this little chip down here that's holding all of these traps, and they set the trap potentials just right so that they can actually trap a chain of these little ions above this chip. Okay, so this area of thinking about how can we actually get the electronics to trap these ions in an integrated, a scalable way, that's been pretty well explored. But now the question comes, as we just talked about a couple of minutes ago, is we have these ions here. Now we need to actually switch their states. We need to read out their states. We need to do these operations, and all of that is done optically. And the problem is, so we have this nice little integrated way to trap the ions there, but we still have a huge optical table, multiple optical tables of bulk optical components that are going to be required to interface with these ions in this ion chain. So now if you go into kind of a state-of-the-art trapped ion lab, this is kind of the view you'd see. There would be an optics lab about the size of this front area here. And in the center, there would be a cryostat, which I think you guys have already talked about a little bit. This cryostat would be cooling ions down to a very low temperature. And then there would be little windows on the side of that cryostat, literally windows. And then we have a whole room filled with optical tables with bulk optics that are taking different wavelengths and polarizations of light, phase-stable light, and bringing it in through those windows to interface with the ions that are sitting in this cryostat quantum computer. Right. It looks super cool. It's also a little bit scary. I go into our collaborators' labs that are working on this, and you're like, don't breathe. There's all these bulk optics all perfectly aligned, and hundreds of components all required to interface with these ions. So the problem is that how is this scalable, right? You have a whole room worth of bulk optics just to interface with maybe tens of ions in this cryostat. If you want to scale up to tens of thousands of ions, many qubits, just like was really emphasized by our previous speakers, that we need to scale up the number, this is not going to be a scalable way to interface with those ions. Right? The hardware is not scalable. It would take like a mall's worth of bulk optics to figure out how to do that. Also, the more pressing problem right at the moment is that when we talk to our friends in the atomic physics world, all of these optical tables are vibrating slightly differently. Right? They're all sitting in the room, vibrating slightly differently. The bulk optical lenses are all vibrating slightly differently. And when all these different wavelengths and polarizations of light now come in to interface with our ion, the coherence of those optical beams is going to be messed up. So you can imagine if things are vibrating slightly differently, the light as it's coming in is going to have a slightly different phase as it hits your ion. It's going to mess up the coherence, which reduces the fidelity of your quantum operation on that ion. So there's really a need to think about a way we can take all these optics and make them more scalable and also phase stable to improve the coherence of these operations. And the solution to that is what we talked about right at the beginning. Can we create computer chips now, these photonic chips, that have integrated photonics components, that have all those optics, but now integrated on your chip to interface with your ion? Maybe we're seeing where this field of integrated photonics can come into play. So what that looks like is now we have this chip here. You can see these metal lines, the yellow. Those are going to be those RF electrodes that are actually going to trap your ion electrically above your chip. The ion is shown here in light blue. So we've again, like I mentioned before, this is a pretty well-known technique, this Paul trap on chip. But now we need to have all these optical beams interfacing to the ion also coming from our chip. So here we would have our integrated silicon photonics waveguides coming in. These would be our tiny little optical antennas that are going to emit the light up and out of the chip and to the point where the ion is trapped there above the chip. You'll notice that these, in this rendering here from our friends at Lincoln Labs, they've colored the beams in different colors, and that's because we actually need different wavelengths or different colors of light to interface up to the ion to do different operations on the ion. So this requires, the different operations that we're thinking about here is cooling the ion. So you trap the ion there, now you need to cool it down to kind of stabilize its motion. Then you have to do state preparation, so initializing what state, is it a 1 or a 0 that ion is initially in. You need to do state excitation, right? When we actually want to perform operations on that qubit, we need to excite different states. And then also optically, we need to read out when the ion actually fluoresces out a photon. When it drops down between states, we need to read that photon out and also capture it optically. These are all optical operations that now we can think about doing on one of these silicon photonic chips. So we'd have this chip here. What this is going to physically look like in our larger system is this photonic chip would be sitting down here. This would all be in a cryostat. Your ion actually is flipped down underneath the chip here. And then you'd have some optical fibers bringing light from an off-chip laser and coupling it onto this photonic chip, and then you would do all your operations that you need to do on your chip, doing all that light delivery to, in this case, this would be a single ion, but of course we can also scale up to multiple ions. And one of the very key components for this is these optical antennas on chip. So what that would look like is you'd have your silicon photonics waveguide, that dielectric waveguide that's confining light on your chip. And then you'd have some little, what we call grating coupler or grating antenna that is going to take that light off the chip and then scatter it up to your ion. What that physically looks like is you have your waveguide and you pattern these little perturbations in the waveguide. That causes scattering at each of the perturbations. If you design them just right, you can get all that light to emit up and to the ion through those metal electrodes that we patterned earlier. So how do you actually make this concept come to life is, again, you need platforms to actually fabricate these photonic chips in. So what that could look like is, here's an example of the platform that we fabricate in. You have different waveguiding layers. This is a silicon nitride waveguide. You could have multiple layers that would allow you to maybe cross the waveguides once you start scaling up to larger numbers of qubits, have different operations happening in these different waveguides. Then you have these emitters that are emitting light off the chip up to the ion that's sitting above the chip. You could have some modulator layers, like we talked about earlier, maybe modulating the light that's actually in that chip. And you could even have these modulators connected to integrated CMOS control electronics on that same chiplet. So really thinking about how can we scale up these trapped ion quantum computers. So the advantages of moving to integrated photonics for this, like we talked about, is the coherence and the scalability. So here, this is nice work coming out of Lincoln Labs a couple of years ago. They actually did an experiment where you can see if you have your ion trap chip sitting here, it's trapping your ion, in this case, below the chip, and then you have free space beams coming in from all those free space optics. Those free space beams are all vibrating differently than your trap chip. And that's what's going to cause this reduction in the coherence, reduction in the fidelities of these operations. When you move to integrated, now you have the light coming in, and it's actually emitting off of the same chip that the ion is registered to. The ion is trapped to that chip, and now we're going to emit all of the optical beams off the same chip. Everything is going to be nicely vibrationally stabilized. You're going to improve your coherence. You're going to improve your fidelity. And then I just love this video showing how we could think about scaling these systems. Let's see if we can play it. So far we really thought about just interfacing to a single ion. That would be like a single qubit in this system. We want to really scale up to multiple qubits. So here would be our single ion. It would be sitting above all these grating couplers that are emitting light off the chip. Then you could shuttle that ion between these different sites. Right? And now you could have gratings that are interfacing to this single ion. And now you can envision creating a kind of gridded up version of this where you'd have multiple sites. Your ions are shuttling between these sites. And that's really what's going to get us to the point of scaling up this trapped ion quantum system concept. This would be really hard to do if all those light beams were coming from off-chip bulk optical components. So of course, we can never talk about research without sending a big acknowledgement to all the other work happening in this field. So I kind of highlighted here the work happening by our collaborators at MIT Lincoln Labs. Initial work kind of spearheading a lot of this integrated photonics for trapped ions was done here at MIT and Professor Rajiv Ram's group in collaboration with MIT Lincoln Labs, the team led at that time by Jeremy Sage. And then we have seen an explosion of excellent results coming out of many groups around the world. Some great work coming out of ETH Zurich and Jonathan Holmes' group, an Oxford group doing excellent work also in integrated photonics. Sandia has a lot of efforts in this space. Cornell, there's a new PI that's working in this space. And then even when we look more broadly, right, we have all this research happening, but now there's been an adoption of these techniques in the industrial space. So we see companies like IonQ coming up that are not just thinking about scaling up ion traps, but also bringing in the integrated photonics to interface optically with those trapped ions. Quantinium is another company, Honeywell, all doing excellent work. I wanted to highlight really quick the work happening in our group here at MIT by all of my excellent students. This is all done in collaboration with MIT Lincoln Labs. So all the previous demos that we looked at were all thinking about interfacing with these ions with just maybe a single beam of light, a single polarization, which limits the functionalities that we can get out of these trapped ion quantum systems. So what our group has been focusing on in collaboration with Lincoln Labs is enabling polarization-diverse integrated photonic beam delivery to enable more advanced functionality. This has been done in bulk optics, but so far hasn't really been touched by integrated photonics. So first thing that we were looking at is what are different architectures where we have these multiple polarizations of beams coming out, what can they actually enable? And one thing is, I mentioned that one of the main functionalities of optics in these trapped ion systems is cooling the ion to low temperatures to stabilize the ion. Fundamentally, this cooling is usually limited to what's called the Doppler limit. If you've heard of Doppler cooling, there's going to be a floor to how cool that ion can actually get. What you can do, instead of being limited by this Doppler limit, is if you have multiple polarizations of light, you can incentivize cooling to sub-Doppler floors. And what that would look like is you'd have this chip sitting here. You'd have these gratings emitting light out of the chip, but they wouldn't just be emitting a single polarization. You'd have two different polarizations of light coming up to the ion. This creates what's called a polarization gradient, which induces different transitions in the ion and enables this sub-Doppler cooling using a technique called polarization gradient cooling or electromagnetically induced transparency. To enable that, we have to think about devices on chip that are going to prepare these different polarization states. So here's nice work led by my students, Ashton and Tull, where we showed the first integrated polarization splitters and rotators on chip that operate down at the visible wavelengths that's required for this. Then my student Sabrina, with help from Ashton and Milica, designed these grating couplers that now don't just emit TE polarizations of light, but emit both TE and TM. So you have to do a lot of different electromagnetics device design to enable this. And again, this is the first gratings that can actually emit both polarizations to interface with ions. Sabrina then took these chips where we have these multiple gratings emitting different polarizations. And with the help of the MIT Quanta group, a postdoc Ethan and graduate student Felix, they took these chips, put them in the cryostat, and actually trapped an ion above the surface, and then induced this polarization gradient using these multiple polarizations of light to show the first polarization gradient result with integrated photonics. And here we're actually able to now cool 4 times below the fundamental Doppler limit with this kind of system, which we're really excited about. And then also, we mentioned how another operation that we need to do with optics for ions is to not just excite different transitions for cooling and state preparation and excitation, but also to be able to collect photons that are emitting out of the ion. And to do that, we have to design what we call collection gratings. So your ion is sitting up here. It's emitting a photon out. You need to be able to collect that photon with some integrated device and then bring it to a detector to be able to understand what the state of that ion is. So here, again, in collaboration with the Quanta group, we showed the first integrated collection gratings for ions. I hope this gives you a flavor for where we can go with this field in general. Maybe now for just the last couple of minutes, I'll briefly switch gears and just mention very briefly some of the other research directions in our group, just to give you a feel for what else you can do with silicon photonics beyond interfacing to these qubit trapped ions. So one of our research directions is thinking about, can you create these silicon photonic chips that emit light off the chip, scan those optical beams around, light gets reflected back and is received by the same chip to enable non-mechanical solid-state-based LiDAR for autonomous vehicles. This is work led by my students Daniel and Ben with the help of Milica. Another area where silicon photonics can have a huge impact is in displays. So here, Milica, with the help of Andres and Henry, is creating a chip that is actually transparent and can sit in front of your eye. And it has all these integrated photonic components that emit light off the chip and actually project 3D holographic images for the user to see for augmented reality. To enable this, we need to think about how can we create these chips that can actually sit in front of the eye. Before everything was, all these silicon photonic devices were focused on silicon wafers that are not transparent. So here we showed the first demonstration of 300 millimeter silicon photonics platform that's actually transparent. We also have to think about modulators for all of these applications and even for trapped ion quantum systems. So here, Milica led the demonstration of the first liquid crystal-based modulators that enable compact visible light modulators on chip. We can also think about silicon photonics to create 3D printers. So the idea here is to have a chip that sits in the palm of your hand and actually projects three-dimensional holograms into a vat of resin to cure 3D objects without needing all the complex optics that's normally required for high-resolution resin-based 3D printers. So this was creating a portable chip-based 3D printer. We can also create chips that emit light off the chip to trap and manipulate biological particles. Here, work led by my student Tal with help from Sabrina and Milica, we were actually trapping and manipulating cancer cells on chip. When we think about biophotonics, we have to create wafers that don't just sit on the body, but that mold to the body or maybe get integrated in textiles, so they have to be flexible. So here we're showing the first 300 millimeter flexible wafers. And then finally, we can create chips that actually are going to transmit data, high-speed data, through free space channels. So here, work led by Daniel and Milica, we're actually creating chips that emit light through water and enable underwater communications. So again, just to give you a flavor for the work that we can do with silicon photonics, the impact we can have outside of just quantum computing and quantum sensing. So with that, I'll wrap up. We started out with just giving you a flavor for what is silicon photonics. We then took a look at silicon photonics for trapped ions, right, motivated by this need for interfacing to ions optically to enable these different functionalities, how we can create these devices and platforms to enable integrated addressing of ions to improve scalability, fidelity, and really find a way forward for trapped ion quantum computing that's truly scalable. And I just very briefly introduced you to some of our other research directions. Of course, I could never give a talk without giving a huge shout out to all the wonderful students in my group. All their wonderful work is really what enables all of this work to move forward. And specifically for this talk, I'll highlight our collaborators at MIT Lincoln Laboratory, led by John Cervini. And John also spent some time here at MIT in the quantum group led by Ike Chuang. So it's been a pleasure also collaborating with the students in that group in addition to the team at Lincoln Labs. So with that, maybe just because we started a little bit late, maybe I'll just pause for one or two questions and then hand it over to Kevin so we can get back on time.
How do trapped ions encode quantum qubits, and how do you do 1 and 2 gate
operations? Yeah. So, yeah, sure. I'll repeat it. So the question here was how is the actual encoding of these operations done on the ion, and maybe how you could scale up to multiple 2 qubits gates or things like that. So the way that we actually encode information on these ions is in their state. So like we were very briefly mentioned earlier, normally this ion is sitting here in some band on your atom. And depending on what band that ion is sitting at, that's going to essentially correspond to a 0 or a 1 in your quantum computer. It's going to correspond to the state of the ion. So how you encode which state this ion is sitting in is exactly with these optical beams that are going to kick that ion up in energy to a higher, further away from the nucleus, or they're going to kick it down. Sorry?
What about phase?
Yeah, so you would kind of create these. You would encode the state using these optical beams, and then if you actually wanted to go in and create higher order gates, then you could take two ions, bring them, interact them together, just like we saw in that quick video I showed. So the two ions would then be shuttled together, they would interact, and then they'd be shuttled back, and then they could kind of go in and interact with other ions in this array of qubits there.
How do you control what it is how they interact, right? Because that's how you see what the gate is.
Yeah, and that's all done optically. So that's going to be, often you would even have two different species of ions. So you could have, for example, strontium and barium. And these two different ions, they're going to require slightly different optical frequencies to switch between their states. And so how you actually excite these different operations is you would choose which optical frequency you actually excite up to the ion to decide what operation you're doing. Yeah. Maybe just for the sake of time, Kevin, maybe we should switch just since we got started a little bit late here. But I think there's going to be plenty of time for more discussion later on when we sit together as a panel. Wonderful. Well, thank you so much.